Our next speaker is Valkyrie from UC Berkeley, and she's going to talk about Maker's Marks, physical markup for designing and fabricating functional objects.
So you know it's a well-designed session when you feel like the presenters before you give 40% of your talk before you even get on the stage. So you'll have to bear with me. But yep, I'm Valkyrie from UC Berkeley, and I'm here to present on behalf of myself and my co-authors, Sean Follmer, Jingyi, and my advisor, Bjrn Hartmann. So our interest is in allowing novice makers to tangibly create interactive objects. Sounds familiar. So we built Maker's Marks, a tool which allows makers to sculpt geometry, select components from an annotation library, sounds familiar, and adhere them to their design. The system then detects these marks and creates mounting geometry, leading users to a final interactive prototype. So although this isn't a math talk, we're going to talk about an exciting number, which is $1799.99. It's the price of a quite reasonable 3D printer, consumer grade. About 35 years ago, personal computers were just hitting this price point, and that's when their popularity started to explode. So today we see 3D printers moving out of the workplace and into museums, hacker spaces, and even libraries, as Stephanie has told us. And those without physical access to a 3D printer can still order their objects to be fabricated off-site and mailed directly to their homes. But there are still some big questions, which I think this whole community is wrestling with. What can people make with these machines, and how do they design those objects? So what are people making? Modeling experts create detailed models like this one that fixture together with existing hardware. Or this one, which integrates a printed circuit board and electronic components. This and the exoskeleton are functional objects that aren't simply static once they're fabricated. Novices, on the other hand, make simpler objects that are more or less self-contained. They can be fun, like these Minecraft keychains, or they can even be useful, like these resizable sorting bins. But they aren't what we'd call functional. We want to support these users in creating objects with mechanical functionality, as in the exoskeleton, and interactive functionality, as in the video game controller. Then there's the question of how users make things. Experts often use function-driven direct manipulation tools like SolidWorks, or there's code-based systems for programmers who would like to get into 3D modeling, whereas novices typically use tools like Tinkercad, which have them drag and drop primitive shapes onto a workpiece and resize them by hand. Prior work from our community has explored more direct methods of interacting with 3D objects, like annotating physical versions with special pens, or even allowing users to employ physical objects as stamps to build up a model. And certainly no interactive prototype is complete without electronics, so other work has explored tools to digitally design and fabricate laser-cut enclosures for electronic components. We're excited about the prospect of including functionality in prototypes, and we want to focus on the way that many people already know how to model, which is using their hands. We did an exploratory user study with several participants from our institutions. We had them design a few objects, including a mount to hold a cell phone to a bicycle, in 3 different conditions: sketching, sculpting, and sketching and sculpting together. We noticed something interesting across all 3 of these conditions. When our participants couldn't draw fine enough details to express the designs they wanted to make, they created annotations in the form of callouts to describe their designs further. Similarly, in the sculpting condition, when users were unable to express their ideas in clay, they also used annotation. Here, the green dot indicates that these 2 parts should be joined, while the clay wasn't sturdy enough to hold itself in this configuration. The system's premise comes from using hands to create rough geometry and the machine to create precision geometry. Thank you. So let's look at an interaction scenario. This is Anne. She's 12, so she doesn't like much, but she does like her wolf-stuffed animal, Woofles. Unfortunately for Anne, so does her mean big sister. Anne wants a way to keep Woofles safe. So she grabs 2 toilet paper rolls and some masking tape to start designing a box. She tapes together the rolls, and she puts some paper around the outside to make it smooth. After that, she molds a mine sign out of clay and sticks it onto the front. Now Anne adds her annotations. She needs buttons to enter a secret code and a gyro to sense when the box is open. She'll also use a hinge to support opening the box. and 3D scans her box and cleans up the mesh. Right now, we use a desktop 3D scanner, but in principle, any photo-based scan would work, for example, 123D Catch. Then she imports it to the Maker's Marks tool, where she selects that she doesn't need bosses, but she does want a lip so the box closes nicely, and we'll talk about those later. The tool takes her scan file as input and generates an STL, which she can send to her 3D printer. After printing, she'll snap in her electronics and program the functionality that she wants. Many tools from our community, like Scratch or LittleBits, could help her with this task. Once the code is uploaded, Anne's sister can't take her wolf without setting off an alarm. Oh, I don't have sound. Shoot. Well, button, wah, wah, wah. And Anne knows that Wolf's is safe. Happy sound. So let's talk about the implementation. Users first create their models in the real world. They can be created from any materials, like paper, tape, and clay, existing 3D objects, or clay on its own. All of Maker's Marks' processing is based off of a 3D scan of this real-world object. The scan is composed of geometry and a series of texture images. So our first processing step relies on the texture images. We use computer vision to search for annotations in our image. Our annotation library contains electronic components, like joysticks and buttons, mechanical components, like hinges and knobs, and pure geometry components, like holes and parting lines. Some of our components have unique features, like the speaker. It's not purely functional, but it has an aesthetic component to it in the form of a configurable grill that slices through the surface of an object to let the sound escape. Also, our servo is a two-part pair that attaches separate objects together with a movable servo joint. But anyway, let's say we're looking for the location of this joystick. Our marks are designed for human legibility, displaying the name of the component as well as an image of it. They have an identical footprint to the component itself to aid in space planning. Also, our marks have these computer vision-friendly designs, which is what we're going to be working with. For adding multiple joysticks, we do have to use multiple unique joystick marks. We differentiate between multiple instances of a mark with different fonts and vector graphics. So, to find this joystick, we do SIFT key point detection on the mark as well as on our texture images. We repeat this for every image that's in our texture map. And then we use random sample consensus, which you may know as RANSAC, to find the best image in which the joystick appears. With this in hand, we remap our 2D texture locations back into 3D space on our geometry. This is done by interpolating the pixel locations and using the texture mapping functions that are defined in the scan file that we got earlier. For each component, we store 3 different kinds of geometry data. We store a 3D model of the component itself, a clearance model that includes space for cables to come out and attach, and a mounting model that we're going to add to our final geometry. But right now, we're just going to look at the clearance model. We calculate the translations and rotations that are necessary to align our component geometry to the annotation counterparts. We do this for every part in the object. Then we slowly push them backwards along their normals, 1 millimeter at a time, to see if they intersect with our object's shelled body. This ensures that our parts are going to sit inside the object rather than on its shell. Then we check to see if any of our components' clearances intersect. In most cases when this happens, we just inform the user, but for non-input components like the microcontroller, we can do something else. We push the component back outside the object and create extra space for it so that it won't interfere with the other components. This results in final geometry, which we then subtract each model's access geometry from and add all mounting geometry to. We have 2 options to help assemble models after printing. First, we're going to talk about bosses. So we create a uniform field of bosses for an object, and then we prune it to remove all the bosses that intersect our components. And finally, we cut the field to fit inside the object and intersect the geometry so it doesn't stick out. When they're printed, these bosses can be fastened together with screws and threaded inserts. Our other assembly option is generating lips to help with alignment. So along a parting line, we'll expand the geometry at the line up and down, and then we'll create a small offset inside, and finally add a square lip to the interior that will fit tightly with the upper part. So here's the lip geometry from Anne's box, visualized in 3D on the left and printed on the right. Finally, after the processing is done, users print their object and snap in their components, and then they can program interactions and test out their designs. So to explore the space of prototypes enabled by Maker's Marks, we created several objects. I've already told you about Anne's safe box, and I walked you through the video game controller's processing. In addition to these, we created a two-part bust of Left Shark. The bust and fin were sculpted separately, and they're linked now by a servo. Now Left Shark's IR rangefinder can detect nearby people so that he can wave. Finally, we extended the nose on a potato-shaped toy and marked spots for Raspberry Pi in the body and a camera inside the nose. We set it up as a fun baby monitor. So now I'll talk briefly about some drawbacks of our technique, as well as future work for us. So first, adhering stickers has limited precision. So building a precise prototype can be challenging. They don't fully conform to the undersurface, and in fact, they interfere slightly with the scan geometry. Right now, it takes an expert to clean up the scans to make them usable, but the future will hopefully see improved scanning software or even send-away services for things like this. Our technique requires the use of a parts library. Some parts manufacturers already provide 3D models of the parts, and we're interested in techniques for synthesizing the mounting geometry rather than requiring that it be modeled by hand. We'd also like to explore marks for non-part geometries. For example, they could express surface textures, as you heard about from Cesar on Wednesday. And finally, in the spirit of the keynote, we are planning to open source this technique. I'm actually graduating soon, so be on the lookout for all of my prior work to appear on GitHub. Thank you very much. I'm happy to take questions.
Questions from the audience? So you mentioned that you had some users for the user study. I was just curious, what was their background? Did they have design background, or were they entirely novice users?
Some of them had design background, but some of them were researchers. So we actually, well, the details are in the paper, but some of them were like expert designers, and some of them were quote-unquote novice designers. So it was a range of experience, but we saw the annotation used by everyone.
Hi, Danny Lashbrook from the Rochester Institute of Technology. I'm curious about the assembly process, if there's anything that can help the novice user in understanding what to put where.
In the sense of like what components they need, or?
Well, you've got a bunch of buttons and you've got a microcontroller, and maybe there's some other parts that go in there, and some of them are obviously UI components like the buttons and LEDs, but some of them are not, like the microcontroller, and so they probably didn't place the microcontroller purposefully, so how do they know what they need to put where and how to hook things up and so forth?
Right. That's an excellent question. So that's another, actually I didn't even mention this as a limitation, but that's another limitation of the technique, is that you have to explicitly place everything. So things like the microcontroller, which can just be totally enclosed, you have to say, you know, where it goes, quote unquote. And I think that there are opportunities there for using this design tool in a different way, but we were really focused on this like tangible modeling piece. I think that there's a lot of, well, obviously there's a lot of interesting work in other ways of sort of tangibly modeling these things and helping users understand how to make something good.
Thanks, very cool work.
Thank you.
So how do you specify the logic? Just standard coding?
Yes, just standard coding. So we don't do the logic at all. We are relying on .NET Gadgeteer right now as our components, because they have these very regular sort of mounting holes on them. But yeah, in principle, you know, using Scratch or some other like accessible programming language would probably be the best option for novice users.